So, round of applause for Jon with Evil Go, doing well by doing bad.
All right, hello Gocon Canada. By the way, you might have seen one of my slides already today, once or twice, so we'll get to that point and you'll know what I'm talking about. My name is Jon Bodner. I'm a software engineer at Morning Consult. After decades of programming in Java, I've mostly been working in Go for the past several years, and I suspect not all that uncommon. I mean, how many people here used to work in another language, still do work in other languages? Yeah? Now, working in Go, it's great, primarily because the code is so easy to follow, right? Without inheritance or manual memory management or function overloading, operator overloading. Go just encourages a simple, straightforward programming style. And straightforward code is readable code, and readable code is maintainable code. And that's great for my company, for my coworkers. But what about me? You know, I started to wonder if all this easy to understand code was in my best interest. Maybe I did want some unmaintainable code. After all, unmaintainable code is job security, right? So how could I bring bad design to my Go programs? And then I thought, I bet there are other Go developers out there who want job security too. So I put together this talk to cover everything you can do to make your Go code as hard to follow as possible. We don't have time to cover all the ways you can make your code terrible, so let's just talk about a few. And they are poor packaging, improper interfaces, passing pointers for population, propagating panics, side effect setup, and frameworks for functionality. Sorry, got that out of order. In order to properly do evil, you do have to know how to do good. So we'll go through these points one at a time. We'll see how goody-goody programmers do things, and then we'll see how to be evil. All right, now packages, they're a nice place to start because they're so unassuming. I mean, how can organizing your code make a difference? Well, in Go, the name of the package is part of the name we use to refer to the items. We write things like func.println or HTTP register func. And because the package name is so visible, good Go developers, they make sure the package name describes what the exported items are. So you shouldn't have packages with names like util because you want to write things like util.json marshal. You want to write names like json.marshal. So good Go developers, they also don't create a single DAO or util package, a model package. And for those who aren't familiar with the term, a DAO is a data access object. It's that layer of your code that talks to the database. And if you have a single library for your company with all of your DAOs, it means everyone's going to share this one single dependency. And the more of these single dependency choke points that you build up, the more likely that you end up creating a cyclic dependency between packages, and Go doesn't allow those. And you also end up with something even worse than that, a situation where a change to support one of your microservices requires you to upgrade all of your microservices at the same time, or else something breaks. And that's called a distributed monolith, and it's really hard to do updates once you've accidentally built one. So it's easy to be evil here. Organize your code badly and give your packages bad names. Break your code up into packages with names like model and util and DAO, and then when people end up with cyclic dependencies or distributed monoliths, you just get to sigh and tell them this is doing it all wrong, you know? So now that our packages are all messed up, let's move on to interfaces. Now, interfaces in Go are not like interfaces in other languages. The fact that you don't explicitly declare that a type implements an interface seems like a small detail at first, but it actually completely flips around the concept of interfaces. And let's take a look at why. So in most languages with abstract types, the interface gets defined before or alongside the implementation. And you have to do this because sooner or later, you will need to swap in a different implementation of the interface, if only for testing. And if you don't create the interface ahead of time, you can't just go back later and slip in the interface into all that code that uses the class, because it has to be rewritten now to refer to the abstract type instead of the concrete type instead. And so for this reason, Java code offers these giant service interfaces with tons of methods on them. And classes that depend on these interfaces then use the methods they need and just ignore the rest. And writing tests is now possible, but you have this extra layer of abstraction, and you have to fall back on tools to generate implementations of all those methods you don't even care about when it comes to test time. So in Go, that implicit interface defines what method you need to use. It's the using code that owns the interface, not the providing code. So even if you're using a type with tons of methods defined on it, you can specify an interface that only includes the methods that you need. And different code that uses different parts of the same type will only define an interface to cover the functionality that they need. And these interfaces only usually have a couple of methods on them too. And this makes your code easier to understand, because not only does your method or function declaration define what data it needs to use, it also defines exactly what functionality it's going to use. And that's why good Go developers follow the advice of accept interfaces, return structs. But you know, just because it's a good practice doesn't mean you have to do it, right? So the best way to make your interfaces evil is to go back to what other languages do and define interfaces ahead of time as part of the code that's called. Define really big interfaces with lots of methods on them that get shared by all of the clients of the service. And that makes it unclear what methods are actually needed, which creates complication. And complication is the friend of the evil developer. So on to our next bit of evil, pointer passing for population. And before we talk about what that means, get a little bit philosophical for a moment. If you step back and think about it, every single program ever written is exactly the same thing. Your program takes in data, your program processes the data, and then the program sends the data someplace else. And if you look at programs this way, the most important thing you can do is make sure it's easy to understand how that data is being transformed. And it's best to keep your data as immutable as possible because data that doesn't change is data that's easy to track. And so in Go, you have reference types and you have value types. Very quickly, the difference between the two is whether the variable refers to the data or to the data's location in memory. Pointers, slices, maps, channels, functions are reference types. Everything else is a value type. And if you send a variable of value type to another variable of value type, it makes a copy of the value. So changing one variable doesn't change the other one's value. Assigning a reference type variable to another reference type variable means they both share the same memory location. So if you change the data pointed to by one, you also change the data pointed to by the other. And that's true for both local variables and for parameters to functions. So good Go developers, they want to make it easy to understand how data is being gathered, to make sure to pass in value variables as often as possible. Go doesn't have a way to mark fields in a struct as final. That's not great, actually. But functions that have value parameters, it can't modify the value of those parameters, so all that function can then do is just return back a value. And then if you populate a struct by calling functions that take value parameters, you then compose the values together into the struct, and you can tell exactly where each value in that struct came from. So how do we be evil? We do this by inverting the model. Rather than calling functions that return values we compose together, we're going to pass a pointer to a struct into functions and let the functions make direct changes to the struct. And since every function has the whole struct, the only way to know which fields are being modified is to look through all the code. And you have invisible dependencies now between your code where data put in by one function is required by a second function, and there's absolutely nothing in the code to indicate that you must call that first function first. If you build your data structures up this way, you'll be sure that no one else will understand what your code is doing. And now we're on to error handling. And maybe you're thinking that it's already pretty evil to have programs with roughly 75% error handling, and I wouldn't say you're entirely wrong, right? I mean, Go has a lot of error handling and it's front and center, and it would be nice if there was a way to make it a bit less in your face, and there are proposals about this. But errors happen, and how you handle errors is what separates professionals from the amateurs. Bad error handling produces unstable programs that are hard to debug and hard to maintain. Sometimes being good means doing the hard work. So a lot of languages, C++, Python, Ruby, Java, others, they use exceptions to handle errors. If something goes wrong, you just throw or raise an exception and someone somewhere will take care of it. Probably. I mean, if even it was possible for the exception to happen, because with the no pun intended exception of checked exceptions in Java, there's nothing in the function or method signature to indicate that the exception could be thrown. So how do you know what errors to worry about in these languages? You have two choices. You can read through all the source code that your code calls, and all the source code that code calls, and so on and so on and so on. Or you can trust the documentation. Raise your hands if you trust the documentation. Okay, I kind of thought so, yeah. So how do we bring this brand of evil to Go? We do it by abusing the panic and recover keywords. Panic is meant for situations like disk disappeared or network card exploded. It's not for someone passed a string instead of an int, but it could be. So, unfortunately, other less enlightened people, they'll be returning errors from their code, so here's a helper function, panic if error. You can use this to turn other people's errors into panics. And once you have panic if error, you can wrap other people's errors, shrink your code down, no more ugly error handling. Anything that would have been an error is now a panic. It's so productive. And you can put a recover somewhere near the top, maybe in some middleware. And so then not only are you handling the errors, you've made everybody else's code cleaner too. So doing evil by looking like you're doing good, best kind of evil. All right, so now we're on to configuration by side effect. And remember, a good Go developer wants to understand how data flows through their program. So the best way to do that is to know exactly what the data is flowing through by explicitly configuring the dependencies in your application. So even things that meet the same interface may have very different ways to do that, like some code that stores data in memory versus code that talks to a database. And lots of languages have ways to magically run code, and Go is not immune to this. And who's heard of init functions, right? I think we may have talked about them today even. If you have an init function, you create a function called init with no parameters. It automatically runs whenever the package is loaded. No need to invoke it explicitly. And just to make it more fun, you can actually have multiple functions called init in the same file or in multiple files in the same package, and they all run. Try it sometime. It's great. And who's heard of blank imports? We talked about these also earlier today, right? So if you have a line like import underscore github.com libpq, and when that does, it imports github.com libpq, runs its init functions, but doesn't give you access to any of the identifiers in the package. And so for some Go libraries, like database drivers and image formats, you have to load them this way by including a blank import for that package somewhere in the code just to trigger the init so the package can register some code. Now, this is obviously a bad idea, right? I mean, you have this code that runs magically. It's completely out of the control of the developer. And using init's pretty discouraged these days. It's obfuscated. It's obscure. It's really easy to hide in a library. So in other words, it's really perfect for our evil purposes. Rather than having explicit configuration or registration of items in your packages, you can use init functions and blank imports to set up your application state. In this example, we're making account available to the rest of the application via a registry, and the account package puts itself into that registry using an init function. So then if you want to use account, you put a blank import somewhere in your program. It doesn't have to be in main. It doesn't have to be in related code. It just has to be somewhere. It's magic. Just put some inits in your libraries and watch people scratch their heads wondering how dependency was set up and how to change them. Say it with me, job security. All right, let's talk some more about configuring your application. If you're being good, you want to isolate the configuration from the rest of your program. You're using the main for your program as a way to capture properties from the environment, convert them into the values that are needed by the components that are explicitly wired together. Components don't know anything about property files or environment variables or how those things were named. And for simple components, you have public properties to set, and if you want to be fancy, you'll have factory functions that will take in the configuration information and return back a properly configured component. But evil programmers know it's best to sprinkle configuration information throughout the entire program. Don't have a function that takes in the values you need. Just take in a map of string to string and say you'll convert them yourself. If that seems too obviously hostile, what you can do is have an init function to load the property file from inside of your package and set up the values yourself. It seems like you've made life easier for everybody else, but you know better. So with the init function, you can define new properties deep within the code, and no one is going to find them until they get to production. Everything crashes because something is missing from the dozen different property files that are required in order to launch. If you want to get extra evil powers, you can then offer to set up the wiki to track all of the properties across all of the different files, and forget periodically to add new entries to the wiki. As the keeper of the properties, you become the only person who can get your company's software to run. Now finally, we come to frameworks versus libraries, and the difference is subtle. Right? It's not a size thing. You can have large libraries, you can have small frameworks. A framework calls your code, you call a library's code. Frameworks require you to write your code just so, whether it's naming your methods in a certain way, or making sure they meet certain interfaces, or make you register your code with the framework. Frameworks just dump their requirements all over your code, and in general, the framework owns you. So good Go encourages libraries because libraries are composable. And sure, every library expects its data to be in a certain format, but you can write a little bit of glue code to massage the output from one library into the input for another. So with frameworks, it's hard to get them to play together nicely because each framework wants complete control over the code that runs inside of it. So oftentimes, the only way to get frameworks to play nicely together is for the authors of the frameworks to get together and put in explicit support for each other's code. And if you really want to gain lasting power through the evil of frameworks, write a custom framework that's only used in-house at your company. It's fantastic. So if you look over all these evil techniques, one theme really stands out. Magic is evil. Anytime you set up data without making it explicit, anytime code runs due to configuration instead of explicit invocation, anytime you make it harder to look at a piece of code, understand exactly what it's doing, that's magic. And what makes magic so evil is that at first it actually looks like it makes things better, because magic usually makes code more concise by hiding important details, making it harder to change those details, or even know they exist in the first place. You're making it more difficult for someone else to pick up your code and make changes to it. So what does it look like if we put all of this evil together? You'd have a framework that uses lots of configuration files, populates fields of structs using pointers, defines interfaces to describe the types that are being published, you relies on magically run code, and it panics whenever there's a problem. And if you go to github.com/evilgo, you'll see Fall, a dependency injection framework designed to bring you all the bad things you could possibly want. And I've paired it with a tiny web framework, Outboy, that follows the exact same principles. And yes, these are real. So you might be saying, how bad could it possibly be? So we'll take a look. Don't have time to go through a big example today, but we'll walk through a simple Go program that exposes a single HTTP endpoint, and then we'll rewrite the program using Fall and Outboy. So our simple program is based on a single package called greet that contains all of the basic functionality to implement our single endpoint. And because it's a sample, we have a DAO that works entirely in memory with 3 fields to hold the different values we're going to return. And there's also a method that fakes our database call, returns back the proper greeting depending on the input to the method. Next comes the business logic, and in order to implement our business logic, we define a struct to hold the output from the business logic. There's also a greeting finder interface to describe what the business logic is looking for in a data lookup layer, and there's a struct to hold the business logic itself with a field for that greeting finder. Actual logic's pretty simple, just calls the greeting finder, handle any errors that might happen. Next comes the web layer, and for that we define a greeter interface that is going to provide the business logic for the web layer, and then we have a struct that will contain the HTTP handler as well as a link to our greeter. And then we have the method to implement our HTTP handler, takes apart the HTTP request, calls the greeter, handles any errors, returns back the results. And this is all pretty simple stuff. That's the end of the greet package, so we'll take a look at how we then build our main. In the main package, you have a struct called config that defines the properties that we need in order to run. And in main, we have this function that's going to do 3 things for us. First, it loads properties from a properties file and puts them into an instance of config. We're running short on time, so I don't have time to go through all the implementation of the load properties, but it's simple, it's up online. Config loading fails, you can report back an error, and then we exit. Next, the main function, it's going to wire up the components in the greet package, explicitly assign them the values from the config, and setting up how one component depends upon another. And then finally, we call this small library. We pass in an endpoint description of the path to be handled, the HTTP verb that we're listening for, and the HTTP handler is going to handle the request, and then the server starts up. So this example is pretty short, but it shows how good Go is written, right? Some things are a little bit verbose, but it's clear what's going on. So you glue together small libraries that are explicitly configured to work together. Nothing is hidden. Anyone can pick up this code, understand how the parts fit together, and then swap in new parts as needed. So we're going to look at the Fall plus Outboy version next. So first of all, we're going to break apart our greet package into multiple packages with each one containing one layer of the application. And this is the DAO package. We import Fall, our dependency injection framework, and because we're being evil and defining interfaces on the wrong side of the relationship, we define an interface called greet DAO. And notice in greet DAO, there's nothing referring to an error. If something fails, we're just going to panic. So far we got bad packaging, bad interfaces, bad errors. We're off to a great start. All right, so next, we see our struct from before, slightly renamed, but we add these struct tags to our field, and they have this key value. And that key tells Fall to assign a value to those fields, that value's been pre-registered with Fall, so we can assign the value to those fields. Method's mostly the same, don't have to look at that one, but we now have this init function in our package as well, and this is where we really start piling on the evil. All right, so in the package's init function, we're going to call Fall twice. Once, register the property file with the values for that DAO, and next, we're going to call Fall with a pointer to an instance of our struct so that Fall can then inject those values into our struct and make it available for other code to use. And speaking of other code, let's take a look at the service layer. So in the service layer, we import our DAO layer because you have to access the interface that was defined there. You have to import a model package we haven't seen yet, but we'll store our data types over there. And it will import fall because, like all good frameworks, it forces itself everywhere. We also define an interface for the service to expose to the web layer. Again, no errors are going to be returned. And the implementation of our service, it now has this struct tag called wire. So what does that mean? Well, any field tagged with wire will have its dependency automatically assigned when the struct is registered with fall. What's going to be assigned to this field? In this small program, it's kind of clear, but in a bigger program, who knows, right? All you know is something somewhere implemented that greet DAO interface. Maybe it talks to a database, maybe someone left behind some test code. It's great. Who knows what's going to happen? So next we have our method for our service, been modified slightly to get the greet response from that model package. Errors have also been completely removed from the code. And finally, we have the init function where we're going to register our instance of our service with fall. So let's take a look at that model package I mentioned earlier. Not much to see here, just the model is separated from the code for no reason other than layering. And then we have our web front end in the web package. Excuse me. And in the web package, we're going to import both fall and outboy, and we import the service layer that our web package depends upon. And because frameworks only play nicely together when they've been designed to, fall has special case code to make it and outboy work together well. We also modified the struct that's going to hold our controller to have two fields now, one that's wired by fall with an implementation of that greet service, and the other that's the path for our single web endpoint. It's assigned the value of a property that's loaded from somewhere, you know. And here's the rest of our web tier. Our HTTP handler is now renamed to getHello. It's error handling free. We have this capital I init method. So this is a magic method that's invoked on structs that are registered with fall after their fields are populated. So in capital I init, we call outboy to register our controller and its endpoint at the path that was assigned by fall. And so you might be wondering, look at this code, right? We have the controller, we've got the path, but nothing in there mentions the HTTP verb, where to go. So in outboy, look at the method's name and use that to figure out what verb a method responds to. Method's called getHello, so it handles GET requests. If you don't know the rules, you can't understand what's going on. Evil, right? So finally, you call the init function, register a property file with fall to get that path I was talking about, register the controller with fall as well. Only thing left to show is how you kick off your program. And so in main, we've got a couple of blank imports to register outboy in our web tier, and then we call fall.start, and that kicks off the whole application. And there we go, a complete program built using all of our evil tools. So this is terrible. We did not plan this at all, by the way. The magic's obscuring how the parts of your program fit together. It makes it far harder to understand exactly what's going on. And yet you kind of have to admit, there's something a little bit seductive about writing code with fall and outboy. And for a tiny program, you could even argue it's an improvement. Look how easy it is to specify your configuration information, right? And you wire up dependencies with almost no code. I registered a handler for a method just by using its name. And without any error handling, everything looks so clean, right? And that's the way evil works. At first glance, it's all really appealing. But as the program changes and grows, all that magic just starts getting in the way. It makes it harder to figure out what's actually going on. And it's only when you're fully in the grip of the evil do you look around and realize you're trapped. And so for the developers in the audience who've worked in enterprise systems before, all the practices I described probably sound horribly familiar. So I don't want to name names, but these are maybe a little bit of name names. But these are the patterns and practices that enterprise developers have been using for a long time. So Brian Kettleson has said the enterprise is coming. And what he means by that is that enterprise developers are coming, right? So I love this picture, but really we shouldn't mock them, right? There's a reason for those bad practices. Some are the result of language choices, and some are just the end result of decisions that made sense in context 20 years ago, but don't make sense anymore. And don't get me wrong, we should embrace the enterprise. Go is designed for programming in the large, for projects that span hundreds of developers and dozens of teams. But in order for Go to do that, it needs to be used in the way that it works best. We can choose to be evil, or we can choose to be good. If we choose evil, we can encourage all these bad habits enterprise developers are going to bring with them. Or we can choose good. And part of our job as Go developers is to understand our best practices well enough to explain the reason why they should be followed. So the only downside of doing good is that you'll have to find another way to express your inner evil. Can I interest anyone in Bitcoin mining? Thanks for your time. Do you have any questions?
Hey, not really a question, just a comment from one evil genius to another. So your little function, panic of error, that's actually my favorite function in Go. And to be serious, if you're writing prototypes, if you're not writing production code, I write that function in every prototype I ever make. But just as a little tip, I love to call it table flip.
Nice. Anyone else? Oh, great. Well, thank you very much for your time.